For this lecture, I decided to build off of the stuff that we talked about in the last one. So we did some PDF analysis on the last, or we discussed PDF analysis in the last lecture, and I will, there we go, move that around. I will bring up those slides just so that they're here, so I can work off of them. There we go. So, yeah, this one talked through a number of the different exploits and everything. We may just end up. This will talk through the stream filters. So I'll just keep this up in case I need it. I don't really think that I'll need it for this lecture. What I'm going to do is I'm going to go through some of the actual malicious PDFs that I have scavenged, and we can look at how some of the attacks are implemented here. So. So let's see, which are these? I'll just start with like this one. This happens to be the smallest of the bunch. So I'll go ahead and start with it. If I remember correctly, this particular one, so I'm going to these up in a second. So this one was one I'm just going to pull up first, actually. So, usually, well, a lot of times what I end up having is I have some automated tools that kind of use a lot of my knowledge that I run these things through. So it's stuff that I've accumulated over time. Trying to automate some of the tedious manual aspects of analysis, but I'm going to do the tedious parts for you all, so you can kind of see what I'm looking at. So I'm going to open up this one, which is actually, if I remember correctly, this one, I think is actually, let me copy this link address. I think it's actually this one. So this ends up being a really helpful example, yeah. Yep. Yeah. So this ends up being a helpful example to talk about some of the heap spray attack that we were using earlier. So basically, what this person did was they wanted to take advantage of this function call. So there's some versions of Acrobat Reader that have a vulnerability in this particular function, and this has something to do with maybe getting the email info from the user system or from the document. I'm not sure. And in doing so, as we said in the last class, the attacker in this case is not able to guarantee, once they exploit this functionality, they're not able to directly guarantee where they want their attack to land in memory. So they're not able to guarantee exactly where control is going to pass after that exploit occurs. So here actually they go and discuss further what happens here. But if you remember, the way that the heap over, or that the, where do I have it? Right here, the heap spray works, is that itself, it's not an exploit. What it is you're trying to control, or you're trying to make sure that you fill up memory with possibly a repeating pattern that ends up being a maybe useful memory address, but also ends up being an instruction that means something. So an instruction that's executable by the processor, but doesn't have many consequences. So an example would be like a really simple arithmetic instruction. I think I have an example of one right here. So for instance, this pair of bytes would actually decode to this instruction. And that, it does something, but it doesn't really have much of a consequence to it. So I picked this example right here because it ends up being a pretty low memory location. What this person found out was that when they were working with Adobe Acrobat Reader, they found that the heap. So this is built from experimentation. So what they would do is they would try and break Adobe Acrobat Reader. They'd run it inside of a debugger or something like that, or maybe even pause it inside of a debugger, which is something you can do with a debugger, and then try and inspect where it was storing its heap data. And so they determined that that the system, or I should say the application heap, so where it's pulling dynamically or where it's creating dynamically allocated memory, ends up living somewhere in these memory regions. So not exactly sure where, but somewhere within the memory region. So this person's goal was to try and fill up all of the space in there with a pattern that meant that, or a pattern that would have the result of after the exploit was successful, the exploit would end up landing at this address, which is 0A, 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 which, if I copy this and then I put it into Python, ends up being the, what is that, 100 and, yeah. So about memory location somewhere around 160 megs. So actually, he's not able to determine exactly where it resides, but feels that after some experimentation was able to find that it resides, or at least this, he can guarantee that that memory area is allocated within the heap at some point. So his goal is to try and fill up as much memory as possible by executing a repeating sequence of operations to try and get it so that if you end up successfully exploiting it and causing a Stack Overflow bug to be exploited, then you end up getting this value written on the stack. So it ends up being a memory location that's in heap memory. And also that happens after you've managed to stage the code that you want the system to land on with a pretty good level of certainty, at least like some copy of that code is located here. So the person ends up describing kind of the basics for the technique here. And this is kind of what I explained in the slide. I think I went and was a bit more wordy in the slide. But basically what happens is they want to fill it up, or I should say they want to fill up the space in front of the code they want to execute. So this variable, I will do this. This variable I've highlighted is called shellcode. The shellcode is supposed to contain the assembly language, that's the data they're trying to execute. And then what they call the no-ops is supposed to contain the sequence of junk instructions, or the sequence of, the repeated sequence of instructions that don't have much of a consequence if they run. They're just going to try and fill memory, and that means that if your memory, or I should say, if your return ends up landing anywhere within that no-ops, whether it's at the beginning or the middle or the end, it doesn't matter. It'll just keep reading the next instruction and executing it, read the next one, execute it, read the next one, execute it. So this person's approach was to create a PDF document. And this is a really common one that people do, is they'll create like a shell PDF document. And then you can actually embed JavaScript code within it. And there's a couple of different ways. I'm not going to completely go over the stuff in here, because I actually have a copy of this PDF over here in my Remnix VM. So there we go. So yeah, there we go. So then I'm looking at it with the text editor. There's a number. I kind of like the syntax highlighting that it gives me, so that's why I'm doing it that way. There are a number of different ways that this can be approached, though. But the basics of the operation are here. So there's a JavaScript object that's at space, or that's at object number 7, and it actually has the functionality, and it's pretty obvious, mainly because they use, say, terms like this. That would be bad. So one feature that I see in here that I would generally consider to be highly indicative of malicious code execution attempt is this one here, where you see a large amount of hexadecimal data, and then it's passed to this unescape function. So generally speaking, you don't see that approach employed too much inside of a PDF, because it would be a very inefficient way of storing some sort of binary data like an image or something like that inside of a PDF. However, because that's functionality that JavaScript supports, the JavaScript interpreter is built into Acrobat Reader and everything else that reads PDFs and supports the JavaScript inside of it, also supports this mechanism. So what I might end up doing is I'm going to do this. Keep doing that, and I'm going to do this. Great. So kind of what I've found is that there's this unescape here. So I'll just put a note in here. And the other thing too that I can see is there's these alternating sequences of alternating 4-byte sequences %u 3C73. So what that is that JavaScript supports you encoding data in these UTF-16 blocks. So each one of these is actually a 16-bit UTF character or Unicode character. And what this unescape feature does is it actually just takes that data that's encoded that way, and it converts it into a byte string that contains the binary data. So this and this, etc., etc., etc. So what this person's doing when they set this up initially is they are first creating the shellcode. So what they did was they actually wrote assembly language that then they compiled to some sort of binary. So I might actually be able to do I can use like NASM or something like that, or even OBJDump to try and create binary data from assembly language. So what this person did is they they basically used a tool like that to generate some binary data from assembly language they had written that was supposed to be code that they would like to be executed after they exploit the Acrobat Reader. So then the next thing they do is they create what they call their heap spray value. And so the heap spray again is minus the shellcode that you want to execute, minus the functional code that accomplishes the goal you want. You want to pad it. You want to put in front of it this large run of bytes that are representing a character. So this person, for whatever reason, decided that they would put a whole bunch of these character 90s in front of it. So that's basically what they're going to do. And then what they ended up doing was they actually put together a loop that basically will concatenate it with itself. So to actually do, so after this runs once, spray value contains 4 sequences. After it runs twice, it contains 8 sequences. And they just keep running this in a loop, and it does an exponential concatenation until the length of it exceeds, for whatever reason, they pick that value, which is going to be 400,000. So they want it to be 400,000 or 4 kilobytes in length. Then what they did was they have this other array that they allocated up here. It's a brand new array. So what they ended up doing is then create 200 slots in this array, each of which is going to contain this 400,000 bytes of data, or 400,000 bytes of data, right? Yeah, 400,000 bytes of data, followed by the shellcode that they defined up here. So they basically make 200 copies of that in memory somewhere. And they found, probably through experimentation, that very commonly, maybe not all the time, there's all sorts of different variables at play here, but very commonly, if they do this sequence, so they make that many copies of it, then they're reasonably certain that at this location in memory, which is the OA, the one that we did in the one that we did here, that location in memory will contain at least one copy of it. So one of those copies is guaranteed with a reasonable level of certainty to be at this memory location. Quite possibly, if they bump this to 400, then they might get a stronger likelihood than it does. And the way that they do this is they'll actually set it up so they load this. This is kind of me talking from their perspective and trying to build this. Is they'll find a way to do this kind of heap spray exercise, and then they'll run the attack, like multiple simulations of the attack in an environment, like an automated environment or something like that, and really just try and figure out what percentage of times did the data I was trying to create actually end up located in the address. And then I can play with this value here. So if I'm not getting a success rate that's high enough, maybe I try increasing this value, or maybe I try increasing this value here, things like that. So they really kind of go to try and really kind of go through a number of simulations to try and figure out, you know, what type of repetition ends up increasing the likelihood that a random exploitation, or not so random, but a arbitrary exploitation of this, you know, Stack Overflow vulnerability is going to actually result in the code they want being located at that memory address.
How come we know the address of the heap? How can one get know the address? Like tentative address. First, the attackers will try to figure out the probable address.
Yeah.
Then they try to do heap spray, and then they attack. Right? Then they try to exploit Stack Overflow, redirecting to this memory.
Yeah.
But how come they will know the probable address of that heap?
Oh, okay. So, so in Windows, when this Adobe Acrobat Reader is loaded in memory, the Adobe Acrobat Reader, when it doesn't have very many other applications to compete with on the system for resources, most of the time it's going to load up with relatively deterministic address mappings for things. So the application executable code is very likely to always be loaded at the same address. And then when you start to allocate stuff from the heap, that dynamic heap is, you know, always likely to be initialized at a default memory address. And sometimes, like, different variables can be introduced, like if target's running a lot of applications or whatever. So what they tend to do is they'll run this exercise through many different environments. And if for instance, you know, they're testing it and they find out that the heap sometimes lives in one part of memory, you know, when Office is running, or a different part of memory when Office isn't running, or it's in a different part of memory depending on a different version of Acrobat Reader and stuff like that. They might actually make this JavaScript code more complex here to actually look for and test those variables. Because as you can see, their heap spray setup and even their shellcode setup is all controlled by JavaScript here. And this JavaScript, though it doesn't have like full control of the system, it does have a large amount of visibility that can allow it to query the environment and look for things. So, so for instance, you might even be able to glean the address of these somehow through the engine too. But you know, in large part, they figured this out through trial and error. So they'll run the simulation under, say, multiple versions of Windows, even depending what their target is, and try and see if there is any consistency to it. The heap spray technique is kind of a way to make, is kind of a way to introduce consistency. So they might have been able to control, because this is a Stack Overflow vulnerability, they have already exercised some sort of control to be able to get some value on the stack that then the JavaScript engine is going to try and return into. But they may not have, or I should say they definitely didn't have any way to guarantee where Java places this in memory. So what they end up doing with the heap spray is they make multiple repetition. They basically allocate arbitrary objects multiple times to increase the likelihood that at least one of those is going to be, you know, is going to be loaded here. And so using this, you know, running this whole setup in a VM that has, or in VMs that have different configurations, and scripting the thing using like AutoIt or something like that, they'd be able to determine, practice, play with the exploit to try and determine if it gets what they want with a relatively good success rate. And so just kind of like a good example, these things aren't always guaranteed to work all the time. If you like messed around with Metasploit a little bit, you'll notice that some of the exploits actually have a ranking on them that say, I think like best or high or medium or low or something like that. And a lot of those rankings that are listed there is actually the likelihood that that exploit is successful. So after they ran it through so many simulations, that exploit, was only 25% likely to land here. So then what a lot of adversaries do is, after they've gotten, I would say after they've driven this, the likelihood of getting this to work up to a certain amount, like say 33% or something, then what they might do is try and figure out, okay, well, how many people do I have to send it to be likely that some, X number of them are going to actually open it, and then some Y number of those is going to be big enough so that at least one or two of them actually gets compromised if they run it in their system. So you'll see like a lot of talk about like mass phishing campaigns and mass cyber attacks and stuff like that. And one of the reasons they do that kind of bulk attack is to try and play the odds. If exploit's only going to work 33% of the time, but you send it to 100 people, and if the 100 people have like a 10% click rate, then maybe you're going to get somewhere between 2 to 4 people who actually open it, and it actually works on their system out of the 10 who, or 11 or whatever, who are likely to open it. So, so a lot of times what I would do, I can go through the PDF parser like we were using before, and I can look at this thing. It goes and dumps out object listing. So what I can do is I can search for JavaScript stuff, right? And so using the search command, I can search for JavaScript. I can also just search for Java like that, because what ends up happening with this is it shows up as JS, and then it also gets listed as JavaScript. The other thing too is there's this action here. So if you remember, we talked about the features that, and this one's a really good example of how all these objects and names and stuff work together. PDF has all these different features, right? So when we went here, we had the start xref is at 784, so that's, or yeah, I think it's, if I remember correctly, yeah, 784, yeah. And then what this does is it shows what the xref data structure is, right? But then it also has a trailer that tells you information about where the root object is. So what this one ends up saying is the root object is actually object number 1, right here, which is of size 8. So that's actually this object right here in the xref, right? So we can go up to that object, and this is object number 1, and it has a size of 8. So I'm not sure what that exactly means, but yeah. But what you can see is that it actually has a open action right here. So it tells where the outlines are, and I forget what the outlines mean. They're irrelevant for this example, but they're just a data type that you can define for PDFs. The pages, so there's an object that talks about the pages, and that's what's over here. And it tells you that, object 4, has, I guess, some listing of the different, the sub-pages and stuff like that. Object 4 actually tells what the parent is, which is this one, so it has a back reference, and then it tells what the contents are. So it says that like this data here has the contents, and the contents of this says JavaScript example. So this is probably a bunch of text that basically has a paragraph within the page that says like JavaScript example. But the interesting thing here too is that it has open action. So one of the features PDFs have is that when you open it, or I should say they have a whole bunch of hooks that you can apply to execute JavaScript code when certain events happen. So some of you have done HTML, JavaScript programming, like for the web browser and that type of thing. You know, you have all of those on-click, onload, like all those different events that you can hook in order to cause, you know, the page to be redrawn or re-rendered or whatever you want to do when the thing's written or when the thing opens. So PDF has a lot of the same things because it's built on a lot of the same concepts. So we can look at this and we can follow the open action all the way down to object number 7. And so here's that JavaScript that we were looking at in object 7. And so it's right here. So generally, when I would look at something like this, you know, this is JavaScript code. What I can do is I can actually take this, and I'm running this inside of Remnix for a reason. So I can take this code, and I can actually go here, and if I want to, I can actually run the code inside a JavaScript that goes and tries to unescape that stuff. And then I can look at it. And so you can see that it's all been unescaped here. What this JavaScript interpreter, so I'm running it inside of JavaScript right now, what this JavaScript interpreter does is it actually displays to you a encoded version of all the bytes. What I like to do a lot of times is actually kind of write this into like a little Python application. So I'm just going to what I'm going to do is I'm going to talk through some of the steps I'm going through here. So the first thing that I'll end up doing is I will just put that, actually I'll just put it here, right? So that's JavaScript. What I can do is I can actually just do, it's still a string, so I can treat it like a string. I just have to convert it, so I have to remove the syntax and everything to make it kind of compatible with Python. Then the other thing that I'll end up doing is I have this special encoding that's really particular to JavaScript. And one of the reasons I'm just doing it in Python here is just I'm more familiar with it. You can do it with any language you want. What I can do is I can actually just extract, so I can remove these Unicode things. But one of the things I will say that you'll want to be cognizant of is that this data here, so this is a Unicode value, right, for this integer. And I'll put 3C73, right? It's a Unicode value for that integer. And if you remember back to our data encoding discussion earlier, that means that the byte values for that you actually want is going to be this. So one of the, you know, this is a common thing that a lot of the, or a common approach that a lot of them will use because it makes it a little bit more difficult to just pull that out. From your perspective, how you'd expect to see the data organized sequentially, what this means is that every 2 bytes are swapped on you. So if I was to just do what I really want to do, which is I want to remove the percent and the U from it and then just have a sequence of the hexadecimal characters like this, whoops, I need to actually do this, all of them. You know, what I'd like to be able to do is walk through each pair of these digits and then convert it to a byte. The problem is that I need to go every 4 digits and then swap them, because the first byte is actually going to be 73 and the second byte is going to be 3C. So in Python, common approach to do that, and I'm going to remove, well, actually I'll just comment these out. This will be useful later on, and I probably want to preserve it for the course page. So a lot of times what I'll do is first I want to output this to a file, so I'll just open and I want to output it as a binary file, so I don't want to have it try and do any ASCII encoding or anything like that. And that's the reason why I do write, and also I tell it that it's going to be a binary formatted file. Not all programming languages require that, but Python, especially using the newer versions of Python, they do. And then what I can do is I can go through and I can basically go across the entire, it's len in Python, I can cross the entire shellcode blob, and I can step every 4 bytes. So I can start at the 0 byte, and then I can increment my cursor every 4, and then I can try and extract every single one of those things. So then I'll just unwind it by doing something like this. So I want to do, I'll just do this. This will be an easy one. Easy button. So what we're looking at here is this ends up being 0, then this one ends up being place 1, then this one ends up being place 2, and this one ends up being place 3. So what I do is I first grab these two, and then I grab the 2 before it. So I'll just leave the 0 there, just because I think it makes it a little bit more readable. So I'll do something like this to try and extract that shellcode. That should work, right? Yeah. I'll just run it through Python too. There we go. So then, what I ended up having is basically a large blob of binary code. So then, I can look at it and I can try and see. So 7.3, 3C, 3F, 3.4. So we'll try and take a note of that over here. And then there we go. So 7.3, 3C, and then 3F and 3.4. So it looks like the what we were attempting to get, the byte swapping, seems to have worked properly. So then what I'll do is I can use something like ndisasm, or even if I want to get creative, use objdump. I'll just use this one, and I'll look at that data like this. And then what I end up having is I end up having disassembly that I can go and navigate through. And so what this ends up, one of the characteristics this ends up having is that the processor has landed on these spots, or I should say, would eventually get to this location, and it doesn't, it may not know what the current execution address is. So it gets to, like, at some point it lands in this location, after executing those no ops, right? Because what happened was we took this shellcode and we padded the front of it with a whole bunch of no op instructions. So, you know, honestly, if we really want to, I could do something like this, right? Just to kind of simulate what we're looking at. Whoops. In fact, I'm going to do that right here, and then so there's those. So then I'll do this again. So you can see, so what it would have had is it would have had a whole bunch of these in memory padding the shellcode, and then eventually it gets to something like this. And this is actually, this is where you can see, if you recall, ndisassemb was actually giving me a different address for this. So it was giving me this address. So it was giving me, I think, 3E before, which is 4 less than this address. So ndisassemb, the disassemblers, recognizing that the address that this jump instruction is wanting to go to is actually a relative address. So ndisassemb assumes that the first byte in my file is 0. So it's saying that when it gets out of that NOP sled, it then wants to jump to byte 42, which actually ends up living somewhere down here, which gets you to the next problem that a lot of times you'll run into, and you'll need to try and unwind. And that is that you need to use this synchronization parameter, which ends up telling it to always start a new instruction at that spot. So now that I did that, I still have this, so all this code is not changed, but now this has been broken up into multiple instructions down here. So I can keep walking through this if I want. What I'm going to do now is switch gears, and I'm actually going to load this up in IDA Pro, so we can look at, we can actually analyze the code with IDA Pro instead. So let me load that up really quick. Here it goes. And so I'll load up a new file, and let me see if I can remember. So what I'll want to do is I'll want to pick the various files, and then I'll pick the binary raw file selection. And this is one of the handy features of IDA Pro. Let me see if I can remember. There we go. So then I want home, remix, 11, and then, or whoops, keep doing that. I actually want work 11. And then this ends up having that object number 7 here. So then I may want to pick this and tell it, say, what processor. What I usually do is I'll pick the Meta PC, which does a pretty good job of selecting stuff. And this gives you the ability to run a whole bunch of filters against it that use a number of different heuristics and other helpful algorithms to try and see if it can find artifacts within the shellcode. So I'm going to go through these and just pick the default things. Tells me here, so this is again from the meta thing, it tells me here the loaded binary can be disassembled in 2 modes, 16-bit or 32-bit. I will say that for any Windows example, you're usually disassembling in 32-bit mode. So I'll go ahead and load that up. And so now, what I'll do, it loaded up the shellcode right here for me. What I'm going to do is I'm actually going to select that first byte that I think is going to be executable. I'm going to right-click on it, and then, let me see if I can remember. Apologies, yeah, so I'm actually going to turn this into code. So if I choose code here from the edit menu, I'm going to tell it to try and interpret from the instruction I'm using as code. And then what it's going to do, you're seeing now, is it's going to walk through, and what it's doing is that sequence of steps that I was manually doing with the disassembler, where I was going through and trying to figure out where the control flow was being passed to. It did that manually, or I should say, I was doing that manually. It's basically doing that work for me in the background. And what it ended up doing was it filled in all the stuff that it feels is executable code with red, and then all of the stuff that is data, it actually filled up with this yellow color. So you can see that now I have this, and it actually also added these handy little, labels as well. So the next thing I can do, I think, is, I can't do that in this one. So I can't necessarily build a really nice looking program graph out of this one in this mode. But what I can do is I can navigate through it, so I can see where it's jumping to different code points and what it's doing at each one of these things. And I can try and take it up. I can try and analyze it to figure out what's going on. So I can also inspect the different different operations that are being done to try and see, what the shellcode's trying to do. So the large amount of work that would go into trying to tear this apart. I'm not going to get into all of it right now. Let me see if it was able to identify any useful strings though. But that's, and so IDA Pro will give you, let me see, yeah, it's not gonna let me do that. There's newer versions of this tool that, and also there's some others that allow you to get nice graphical diagrams as well. So I'll see if I can pass this one through one of those also later on. But that gives a good example of trying to extract shellcode. And as you can see, one of the other things too, so I'll go back to this for a second, is one of the other things about this that helps you, I guess, identify that you're on the right track, so to speak, is that if I'm to follow this, so I got 1, 2, 3, 4, 5, and then I go down here to 42, 6, 7, so I'm counting instructions right now, and then I go down here to 83, which is ASCII just after multiplication, which is another arithmetic operation. Set the direction flag, so I'm at like 8 now, and then jump to A0, which is going to be somewhere down here, so I'd have to synchronize at it. So I'm at like 10 now. The reason I'm counting all these kind of in my head, so this one ends up ORing so doing another small arithmetic operation, and then it goes to F6, which is all the way down here. What I'm doing is I'm trying to follow the program flow and keep kind of a record in my head of how many instructions I've got in that are executable. So if you looked at one of the instruction tables that I gave you, there's a number of instructions that are system instructions, so they're privileged, which means that they would be instructions that Windows would never let Adobe Acrobat Reader run. So if Adobe Acrobat Reader runs an instruction that is privileged, or supervisor mode instruction, then Adobe Acrobat Reader is going to be killed before it can run that. And then you'll probably get a warning. So if this was like random image code or something like that, I would expect that I would be likely to encounter either a privileged instruction or just a no instruction, a junk instruction, after say 10 or 20 steps through this code. So the fact that I've gotten this far, where if I keep going I've probably got, I'm probably like 20 instructions deep now as far as like just one path of execution. That gives me reasonable confidence that I'm on the right path, and I found that I started in the right place that the adversary wanted the CPU to pick up in. And so IDA Pro provides that type of analysis too. If this had gone through and run into a bunch of system instructions and things like that, it would have actually given you some warnings, basically saying that its heuristics tell it, and that's basically what that is, heuristic. They're telling it that this is probably not executable code. So, but basically, pull, this is where they're trying to set up memory before the exploit. So do that sequence of steps to set up memory before the exploit, so that they can have the exploit jump to the location of the executable code. And there's a whole bunch of different ways that they can put it in there. So I'll go and look at some other ones that I have in here. I don't know. I think this one maybe? Yeah, this one. This one also has stuff. I don't think I have enough time to dive into this one specifically and pull out the same like script and all that stuff that was going on with the last one. But what I do have is the ability to go in here and kind of scan through the file until I find this. So and this is one of the reasons why I picked that example earlier on. You'll notice there's like 4 X's and 4 Y's that are right after this EOF in the PDF file, and then following that is a whole bunch of binary data. And so what this is this is actually a marker. So underneath this is some binary data that the system actually, or I should say the exploit, after it starts running a little bit of shellcode that's buried somewhere up higher, it transfers execution to a loop that then wants to scan all program memory and look for a marker like this. So what I might be able to do is I'm going to close IDA Pro. I don't really want to look at it. So, right. So I can go and look through that, or I can make a note of that. The reason I'm noting these things is they're little characteristics that I am extracting from here that are based on some of the prior knowledge that I picked up from the examples that we had in class earlier. That I'm making note of so that I may be able to write some code or write a Yara signature or something like that that can then try and look for these things in future PDFs and tie them together. I don't exactly know what the nature of this is, but I'm sure that if I really wanted to, I could go and start pulling this stuff out, and it would actually mean something. So one other hint that I'll just add is that when I see code like this, especially this, so you can see that this is the alphabet backwards right here with a little bit of breaks in it, and then it repeats again, but every time it repeats, it ends up being kind of slightly offset or slightly different or something. This is usually what I would call a really simple walk down or walk up encryption scheme, which is basically it starts out with like a really simple XOR key, which you're all familiar with. XOR is a reversible operation. So if you XOR something with a number and it gives you a result, and you XOR that result with the same number, it gives you the original. So one technique they use for hiding what they're trying to exploit on your system is they'll either use XOR to encrypt in a really trivial manner large amounts of binary data with a single value, or sometimes they'll use a scheme like this, where every time they step through, they actually modify the key value by In this case, they're just probably subtracting 1 from the key value. So long runs of data like this, especially if they're paired with, what would look like an oddball marker string. And the reason I say this one's oddball is because it happens like right after the EOF in this document. So it really looks like there's something odd going on here, because I wouldn't expect there to be like, basically more data after the EOF. And there is, and one of the reasons there is because this is actually a PDF plus exploit code within a PDF. What I can do is I don't know if I will be able to see it or not. So there. So I can actually look at it and I can find that this code here, followed by this, is actually right here, so 8222. So another thing I can do, actually I don't even have to do this, I can just do this, equals. So what I'm going to do is I'm actually going to use this DD tool, which is just data dump. Skip is the right one, and then like that. No, it's there we go. So then, if I look at that extracted.bin, you can see it starts at that 5 and then has all the data in it. So then what I can do is I can look at it. And I can see that there's 9, 10, 11, 12, 13, 14, etc. So what I might want to do is I might actually just want to try and write like a small program that can try and decrypt this for me, like let's see, 9 minutes or so. And then there'd be like, shellcode in it possibly. So what I'll do is I will just do this. This is very shorthand for loading the data all into one big string in Python. So it's a nice way to load data into Python. And then what I can do is I can do, do that. So I'm going to create an empty string, and then I will just I equals 0. So that initial byte seems to fall on the 0 location, and then what I'll do is I'll do, so it'll be something like this. And then I'll say S equals, S plus data sub C and CHR. So I get the character value or the integer value, and then I XOR it by I, and then I convert it into a character and I add that to S. and then I make I equals I do I minus 1. So do something like that to redo. So do something that to basically have it so I subtract I by 1 each step, and then this causes it to revolve, so it reverts back to 0 every 256 step. And then finally I may do open, bin, write it out. So I'm going to write out the data, and I'm just going to pass it directly to this. And I'm doing this, hopefully I didn't completely mess this up. Oh look, it didn't cause any errors that time. And you can see that I have a decoded bin. It's right here. It's the exact same size as extracted bin. Let's see if there's anything interesting in it. Looks like there's some stuff in here. I'm not entirely certain what all this is, but I can go and analyze it now, and I don't entirely know what all the data is. I'd have to, well, actually, I do have kind of an idea of what this is. So, what we have here, I think, is going to be an exe file. And how I know it is just I know that this format right here is very familiar to me in that it looks like the format of an exe header. So if you go back to some of the, I don't even have to say if you go back, I can actually find one from an earlier example. Right? Yeah, here we go. So if I go back here to week 7 and look at one of these exe files that we're analyzing, I can show you that, let's see, pull this over here. That the data looks very similar. So you can see that it shares this characteristic with these pieces right here. It seems to have 3 bytes up here, but for some reason those 3 bytes look like this instead of what they look like over here. So perhaps I actually need to go through and look at those. Also, it's got this mess of data right here, so these like 4 lines or so of all of this data that's repeating. This one has something like that too going on here. So commonly what I'll do is if I see a pattern like this, I'll just run this, and I'll do like hex, right? So hex to 78, and then so this might indicate to me, let's see, 33. So this might indicate to me that perhaps there was some sort of assumption that was off about my math when I was looking at the data when it was all encrypted. But what I have learned, just from kind of seeing that this pattern here, so we'll go down to about here, is very closely replicated in here. So you can see that even possibly these bytes right here share the formatting that is over here represented by the PE. bytes. Or it might be down here. Well, the other thing too is you can see that there's this large sequence of vacant space that, here, we'll just do it right here, that spans this section here, and then ends right here. And you have the same thing here in the same range as well. So working this backwards, you end up basically slowly rebuilding the executable from the components it was built from, using each one of these things as hints. So this is kind of a rough example of using some of the analysis techniques, that we talked about in the last one, to try and, basically reverse engineer some of the attack. So what I've learned here is that this this particular PDF, 3.pdf, looks like it probably has an exe buried in it. I have to try and get that out. And in the case of 3.pdf, I managed to learn of that, looking at the PDF and identifying that little marker string that was made up of the X's and the Y's. So it's a very odd string to just like randomly have in the middle of that PDF file. Now kind of it's up to me to try and pull this out, but if you remember earlier when I was going through the slides on Tuesday, I was talking about how sometimes they're constrained by how much space they can actually use for their shellcode or their executable code that they can build with the JavaScript, for instance. This is a really good example of that. This exe, ended up, maybe I may have pulled some extra data out, but maybe it's like, 300 kilobytes or something like that long. That's a really big file, and that's something that isn't really easy to embed within and get prepared the way you want it to in a JavaScript. So what they ended up doing was staging that exe somewhere else in the PDF file, and then setting up the exploit to inject shellcode somewhere. So they could predictably deploy like maybe a few kilobytes of shellcode somewhere, so they could execute that, and then that has just enough logic to go searching in memory for the exe file so that it can write that exe file to disk and then launch it. And so in this case, I've been able to, I was able to pull the PDF or the exe out of the PDF. Now it's kind of up to me to go through the iterative steps, which could take hours or something like that, to try and figure out how the heck is this exe actually encrypted within the file. So that's kind of what I'm going through now.